I wish to say something about the difference between Euclidean and modern mathematics from the standpoint of Euclidean mathematics. For though there may be certain advantages gained in modern mathematics, such as that of performing difficult calculations, performing complex computations, anyone that has read Euclid's Elements cannot help but notice that there are certain advantages to Euclidean mathematics which are quite different from those of performing difficult calculations. In fact, the whole project seems to be aimed at something entirely different than performing difficult calculations. A most striking and obvious difference between Euclidean and modern mathematics is that both the geometry and the arithmetic of Euclid consist entirely of syllogistic proofs in language, whereas modern mathematics consists entirely of equations and procedures of calculation. In Euclid, we find no calculations, not in his geometry, nor in his arithmetic, not even in the arithmetic that we find in a few books of Euclid's Elements. Is there anything like calculation? He draws proportions between ratios, which is quite different than calculating with equations. But even within the paradigm of proportionate ratios, the proofs are spelled out in language. They are syllogisms. Whereas in modern mathematics, both geometry and arithmetic are performed within the same substratum of equations, and consist entirely of the procedures of calculation, even within what are so-called proofs in modern algebra and calculus and the like. The steps of the proof are indifferent. They're the same steps which are taken in manipulating the signs of an equation to calculate. The proofs are composed nowadays entirely within equations and are nothing is inferred as a conclusion from two premises. There's not so much as an inference of pure reason, but the same procedures, the steps of a modern proof in mathematics consist of the same procedures as the rules for manipulating equations and performing calculations. Whereas Euclid, the entirety of Euclid's geometry and his arithmetic even, consist of syllogistic proofs in language. Thus, it is no wonder that Euclid's Elements is a sort of compilation of the theorems or proofs of different figures, all of which were associated with Plato's academy. Euclidean geometry, Euclidean mathematics, is a sort of project of philosophers, is a mathematics for philosophers. The students of Plato and their associates were the ones who discerned and composed those proofs with which Euclid, a century or so later, compiled into a string of proofs, the more complex from the more simple, leading back to axioms. As Euclidean geometry, but also Euclidean arithmetic. Euclidean mathematics is a sort of project of Plato's academy. And was both composed by the students and the associates of Plato's academy and studied by those that followed, with the purpose of habituating the mind to reason. Specifically with the purpose of familiarizing the mind with the modes of reasoning. And withdrawing the soul from particulars to universals. For that is precisely how geometry and the study of mathematics is prescribed in Plato's Republic. As something that awakens dialectic, that awakens skill in argumentation, in proof and refutation. Because the proofs in the proofs in Euclidean mathematics exemplify this sort of sharpness which in other subject matters with subjects more difficult to define and more contentious, the same strings of reasoning cannot be so assuredly performed. And because mathematical objects serve as the exemplar even of universals, there are no other universals which are more clear and easier to demonstrate what their essential properties are than mathematical objects, than triangles and parallelograms. then numbers, then multiples and aliquot parts. These present us with a subject matter which most easily conforms to certain conclusions and the processes of inferring those conclusions from doubtless and certain premises, which ultimately are self-evident, the axioms. The Academy of Plato thus fostered a sort of mathematical discipline which show us what mathematics looks like through the eyes of philosophers. These were the most skilled men in argumentation. These were masters of argument, masters of refutation and proof, turned to mathematics. Thus, Euclid's elements are the sorts of fruits of Plato's academy. Thus, look nothing like the complex computations of modern mathematics. For Plato intended mathematics to be a study that turns the soul from particulars to universals and awakens dialectic and the skill of proof and refutation. That was the purpose of mathematics. That is not the purpose of modern mathematics. Modern mathematics, consisting entirely of equations and of procedures of calculations, does not awaken skill in argument, does not turn the soul from particulars to universals, even turns away from the more simple mathematical objects towards more obscure and complex. Thus, George Berkeley, in The Analyst, asked whether the view of modern mathematicians doth not rather seem to be the coming at an expression by artifice than the coming at science by demonstration. Whether the view of modern mathematicians doth not rather seem to be the coming at an expression by artifice than the coming at science by demonstration. And that however useful it may be, it must be considered only as a presumption, a knack, as an art, rather an artifice, but not a scientific demonstration. And in the same work, he said, however useful in mathematical calculations and constructions, the employment of modern analysts doth not habituate and qualify the mind to apprehend clearly and infer justly. He says elsewhere something to the effect that modern mathematicians, modern analysts, being habituated to reason only within the symbols of algebraic notation, are not rather at a loss in reasoning without them, as if that the procedures of calculation do not make one better at reasoning, at constructing arguments and refutations. Whereas that is the purpose for which Euclidean mathematics was designed. There's another quote here by some Steiner that says, geometry stimulates while calculating replaces thinking. And Newton also shared this opinion. Even Newton shared this opinion. There are actually many mathematicians of the 17th century that held the opinion that the workings of algebra were something with a certain deficiency in respect of the modes of reasoning, even to be embarrassed. Newton was embarrassed to publish his works that were, to him, just tricks for calculation, as long division is. Algebra, the use of equations in algebra, were not aimed at furnishing proofs of theorems. We're not aimed at drawing a conclusion from premises. We're aimed for solving problems. Thus, in Descartes, the father of analytic geometry, of algebra, of the algebraic formulation of geometry, in his book titled La Geometry, does not even mention a proof. He definitely doesn't prove anything. He doesn't even mention a proof or theorem of any sort. He presented his La Geometry, his method of algebra, as a method to solve problems, not to prove theorems. And I don't know when people started using algebra to compose quote-unquote formal proofs. But that did not happen in the 17th century. That, I don't think, happened in the 18th century. Newton, in his correspondence with David Gregory, says that he was aware of algebra only as a tool for discovery or of solving problems, but not as of any use for demonstrating proofs. In 1694, Newton expressed to David Gregory that, quote, algebra is fit enough to find out, but entirely unfit to consign to writing and commit to posterity. And Newton critiques Elsewhere, Newton critiques of Descartes' solution of the Papist problem, which he presented in that book, Law of Geometry. He says of Descartes' solution to the problem, which was him illustrating the use of algebra in geometry. Newton says of that solution to the Papist problem of Descartes, that when transposed into words, it would prove to be so tedious and entangled as to provoke nausea, nor might it be understood. So when someone like me doubts whether or not a proof in algebra or calculus, a proof formulated in algebraic notations, when someone like me doubts whether that is even an argument, and someone says, oh, well, you're just... I point to Newton's statement that when transposed into words would prove to be so tedious and entangled as to provoke nausea, nor might it be understood. But Descartes designed his analytic geometry, and he designed his universal mathematics, his universal mathesis universalis, or his specious algebra, as a method to solve problems, not to prove theorems. Descartes said in his Rules for Conducting the Mind, one of the most foundational texts regarding modern physics and mathematics, that these modes of syllogisms are not of our concern. We're not interested in proofs. We're interested in discovering new knowledge. And that the only definite questions, the only solvable problems are those of quote-unquote transmuting ratios so that they might be stated as equations. Transmuting ratios so that they might be stated as equations instead of syllogistic reasoning, instead of proofs. Whereas Proclus, in his commentary on the Elements of Euclid, one of the most wonderful works from an antiquity that we have, says of Euclid that he exhibits modes of syllogisms of every kind, some indeed receiving credibility from causes, but others proceeding from certain signs, but all of them invincible and sure, and accommodated to science. But besides these, he employs all the dialectic ways, dividing indeed in the invention of forms. By that he means dividing, for example, quadrilateral figures into those that are parallelograms and those that are not, and dividing parallelograms into those that are rectangles and those that are not, and dividing rectangles into those that are squares and those that are not. Besides these, he employs all the dialectical ways, dividing indeed in the inventions of forms, but defining in essential reasons, and again demonstrating in the progressions from principles to things sought, but resolving in the reversions from things sought to principles. Besides this, we may view that in its geometrical elements, the various species of conversions, of proportionate ratios, as well of such as are simple as of such as are more composite. And again, what wholes may be converted with wholes, and what wholes with parts, and on the other hand, as what parts with parts. He then says of geometry, that geometry, therefore, is endued with the knowledge of magnitudes and figures, and of the terms and reasons subsisting in these, together with the passions, or he means essential attributes, various positions and motions which are contingent about these. But employing all the dialectical ways, in principles by the divisions of forms from their genera, and by defining its orations, but in things posterior to principles by demonstrations and resolutions. As likewise it exhibits things more various, proceeding from such as are more simple, and returning to them again. Besides this, it separately discourses of its subjects, separately of its axioms, from which it rises to demonstrations, and separately of essential accidents, which it shows likewise are resident in its subjects, or in essential kinds. That is to say that there is a difference, the characteristic manner between the two paradigms. Euclidean mathematics, consisting entirely in syllogistic proofs of language, employing all the skillful means of argument, all the modes of syllogistic proof and dialectic, and aimed at facilitating or habituating skill in the modes of reasoning in order to awaken dialectic. And on the other side, the modern analysts of algebra and the infinitesimal calculus, which consist entirely of equations and the procedures of calculation, in which even the proofs, even where there are quote-unquote formal proofs, each step is none other than the same rules for manipulating equations. That is odd. They look not like arguments to me. And neither their purpose nor their effect is to awaken interest, let alone skill, in argument and syllogistic proof, and dialectic ultimately. That is not awakened in the soul by manipulating equations and performing difficult calculations. Again, George Berkeley said in the Analyst, whether the view of modern mathematicians doth not rather seem to be the coming at an expression by artifice than the coming at science by demonstration, that however useful it may be, it must be considered only as a presumption, as a knack, an art, rather an artifice, but not a scientific demonstration. And however useful in mathematical calculations and constructions, the employment of modern analysts doth not habituate and qualify the mind to apprehend clearly and infer justly. I hear people slander Euclid, and I never hear a defense of Euclidean mathematics. Euclid is exalted by all previous writers. But in this day and age, I'm amazed at how quickly people want to speak ill of such things as the parallel postulate. Without admitting in the same breath that the proposition that follows from that is indispensable. The proposition that a straight line that falls on two parallel lines produces alternate angles equal the interior to the exterior. And how any such thing as that or anything in the first book of Euclid's Elements can be proved algebraically. There's a sort of feigned declamation of Euclid's Elements, as if they're wrong. But they're not wrong. When people talk about parallel lines not meeting, or parallel lines meeting, no, it's not true that parallel lines don't meet. Oh yeah, it's not? It's not true that parallel lines don't meet. And they say, oh, well, there's no straight lines, you see. Well, in hyperbolic schizogeometry, in schizo-hyperbolic geometry, there's no straight lines because we're on the earth isn't flat. Like that's why Plato's Academy said, if you don't know geometry, get the fuck out of here. Parallel lines don't meet. Parallel lines meet. Oh, there's no straight lines, so Euclid's wrong. This whole thing is a sort of unfamiliarity. People are like that because they're unfamiliar with Euclidean mathematics and they're impressed at the sort of complexities of modern mathematics. But the fact that modern mathematics starts into complexities is quite suspicious. That the obsession of modern mathematics is such things as parabolas and irregular curves and conic segments, where they're too advanced, I guess, for the elements of Euclid. All these sorts of devices, the infinitesimal calculus, algebra, these were all designed with concern for incredibly complex, irregular figures. They're not like, mathematics doesn't just go from more beginner to more advanced without going from regular figures to irregular figures. And if you keep going towards irregular figures, you get irrationals. And modern mathematics has thus focused the entirety of the mathematical disciplines on irregularities. whatever they're doing today with matrices and that the focus of all these quote-unquote advanced mathematics are on irregularities. The purpose for which Euclid's Elements was designed was to prove of the regular figures what their essential attributes are. To prove of triangles. I know those seem like kindergarten topics, but they're not. To prove of triangles that they have their angles equal to two right angles, such that all triangles have angles equal to two right angles. And that if a triangle's angles were ever not to be equal to two right angles, it would cease even to be a triangle. That is an essential attribute. Philosophers don't care to contend over the essential attributes of parabolas. And the irregular figures for which calculus is designed. We're concerned of proving of the regular figures what their essential attributes are. When you think of mathematics as being advanced only when it focuses on irregular figures, you have gone through into the indefinite. You are proceeding towards the indefinite. And the indefinite cannot be known. Irregularities cannot be known. And since mathematics has been re-centered on irregular figures, parabolas, conic segments, infinitesimal calculus, and such peculiar, these are trivial complexities with which modern mathematics is concerned. Advanced mathematics is concerned with trivial complexities, trivialities of irregular figures that have no interest to philosophers. Not only do you not prove of anything, any essential property which inheres in that kind of regular figure, but your calculations come to irrational, basically indefinite quantities. Modern mathematics is concerned with trivially complex calculations to which there is no definite answer. A lot of these things are indefinite. Hence, the inclusion of irrational numbers, of imaginary numbers. They're compounding things indefinite. The principles of the Pythagoreans were the definite and the indefinite. The indefinite dyad is the principle also of evil. It cannot be known. What is indefinite cannot be known. An irrational number is indefinite. There's no definite quantity. Nor do we find definite proofs. All we find is notation. All we find is invented notation. A peculiar notation. Which represents what? Often imaginary numbers, the square roots of negative numbers. Oh yeah, are you far more advanced than Euclidean mathematics? With made up notation to express impossible things? They're always they have whole kinds of calculus designed for irrational numbers. Irrational numbers are indefinite. There's no definite quantity which they represent. They're not supposed to be numbers either. And they have other kinds of the infinitesimal calculus, other kinds of analysis meant for imaginary numbers, for the square roots of negative numbers, which are impossible. A negative number cannot have a square root, since any number, negative or positive, multiplied by itself results in a positive number. There can be no square root of a negative number. That's logically impossible. Yet they found some curious notation to express that. And this stuff spreads like trends, like rumor. Now I want to make a second distinction. I should add that the essential difference between continuous magnitudes in geometry and discrete numbers in arithmetic, the distinction between continuous and discrete, is upheld in Euclidean mathematics. The difference between continuous and discrete being fundamental and primary therein. And that is because propositions are proved syllogistically in language. For Euclidean geometry has as axioms the definitions of the kinds of shapes and the kinds of their parts, from which conclusions are inferred regarding their essential attributes, which belong to each kind of shape insofar as they are of such a kind of shape. Continuous magnitudes or shapes are considered insofar as they are continuous, insofar as they are continuous shapes, rather than, as in the case in modern mathematics, insofar as they can be numerically designated in an algebraic equation. Thus, we find no numerical values in Euclidean geometry. Whereas in Cartesian algebra, or analytic geometry, in algebra, geometry is performed by manipulating algebraic equations, the inputs of which are considered not insofar as they are continuous magnitudes, and not insofar as they are of a certain kind of shape, but only insofar as they can be assigned numerical values through measurement and calculation. Calculation, likewise, is something absent from Euclidean geometry, yet is inseparable from the use of equations in the analytic or algebraic treatment of geometry. Thus, algebra is a sort of universal mathematics, which recognizes no difference between continuous and discrete quantities, and performs the same procedures of calculations upon both indifferently. Similarly, in Euclidean arithmetic, the premises which factor as starting points for drawing inferences are definitions of discrete numbers, such as a unit, a multiple, and an aliquot part, so that the conclusions drawn from such premises are propositions of numbers insofar as they are discrete and not of any continuous interval. The distinction upon which the differentiation between continuous magnitudes and discrete numerals refers is ultimately that of discrete numerals. There is no greatest number. Of numbers, there is no greatest, but the numbers increase infinitely, while there is a smallest unit, an irreducible unit, such that numbers do not decrease infinitely. Thus, in arithmetic, the part is prior to the whole, is logically prior to the whole, and greater numbers are composites of logically antecedent parts, which are irreducible. Thus, arithmetic and numbers are infinite in the direction of increase, but not in the direction of decrease, as a unit is without parts and indivisible. And there are no fractions, negative numbers, there's no zero, there's damn sure no irrational numbers. On the other hand, of continuous magnitudes, there is no smallest unit of length, but all lines are infinitely divisible into smaller and smaller lines. Whereas the upward limit of magnitudes is not infinite, meaning only that in continuous magnitudes, the whole is logically prior to the part, such that the whole, being given and finite, may be divided ad infinitum into smaller and smaller parts without limit. Thus, in continuous magnitudes, the whole is logically prior to its parts and is not a composite of logically prior parts. Continuous magnitudes are then infinite in the direction of decrease or of division, but discrete numbers are infinite in the direction of increase or multiplication. On the contrary, algebra does not consider numbers insofar as they are discrete quantities. Does not consider numbers insofar as they are discrete. Consequently, modern mathematics recognizes no smallest indivisible unit of arithmetic. The unit of arithmetic is not indivisible in modern mathematics, and sees no difference in applying what are now called arithmetical operations, or which we might reterm as calculative procedures. They don't see any difference in applying those to numbers on the one hand and shapes on the other. Algebra, in that sense, homogenizes quantity, seeing no difference between continuous and discrete. The rules for manipulating equations are the same, whether the values of the equation represent measurements of continuous lines and shapes, or whether they represent arithmetical numbers, which have no interval. Accordingly, in modern mathematics, the same algebraic equations and the same procedures of calculation are used regardless of whether the subject matter be linear intervals or arithmetical numbers. We see just equations, a universal mathesis, a mathesis universalis of algebra. Algebra is the universal mathematics, not calculus. Calculus is an application, a specific use of algebra. Calculus is a part of algebra. Algebra is their tool. Algebra is the universal mathematics. Everything is formulated algebraically in modern mathematics. And that was the purpose Descartes designed. Descartes intended for algebra to be a universal mathematics, a specious algebra, which we will find other difficulties with in a future recording. Much of the difference between Euclidean and modern mathematics stems from confounding the differentia between discrete numerals and magnitudes of continuous interval. The differences, the problems, the sort of contentions that arise between the two paradigms of mathematics result from confounding the difference between continuous and discrete. Thus, we will find that irrational numbers arise in arithmetic only through incommensurate magnitudes of the diagonal of a square being incommensurate with the side of the square. The side and the diagonal of the same square have no ratio. There's no definite ratio. You can't find any part of the side of a square which measures the diagonal a certain number of times. They're thus incommensurate. And we only find, numbers are not incommensurate. Numbers are all commensurable with the unit. But some lines have no ratio. Have no ratio to any line as any number has to any other number. From which result irrational numbers. The diagonal of a square is incommensurate. There's no ratio. Irrational. Has no ratio to the side. Those things occur between magnitudes, between lengths, between areas. And then modern mathematics, confounding as always arithmetic and geometry, think that they're just trying to find the square root of 2. Question doesn't call for any square root. We're looking for the ratio between the side and the diagonal of the square. We're not looking for a number. They're looking for the square root of the number 2. We're trying to show that there's no ratio between the diagonal and the side of a square. Soon enough, they've invented irrational numbers to account for the square root of 2, of the number 2. We're not talking about numbers. We're talking about the ratio between the side of a square and the diagonal. And they get there because Pythagoras' theorem is that the square on the side the square on the diagonal is equal to 2 of the squares on the side, or better yet, the square on the diagonal is the double of the square of which the diagonal bisects. If you have a square and you draw a diagonal of that square, the square on the diagonal is the double of the square of which it's a diagonal. Thus, considering these things in algebraic notations and numerically, they think that you can find the diagonal, the quantity, the numerical value of the diagonal of a square by finding the square root of the double of the square in question. Square in question is designated as 1. That's our unit. It's not a good unit to look for. It's not a good unit to look for the diagonal because the diagonal's what? Maybe less than 1? Not good. If you're looking for the ratio between the side of a square and its diagonal, you should be looking for the part or the segment of the side of the square. Not taking the square of which the diagonal bisects as a unit 1. Square root of 2. We're not talking about the square root of any number. We're talking about the length of a line having no ratio to the side of the square. Just by confusing the difference between numbers of which there's no interval. There's no spatial dimension of numbers. And shapes, which are infinitely divisible into smaller and smaller lines. A line is infinitely divisible into smaller and smaller line segments. Numbers are not like that. Numbers are not composed on a continuous line. There's no space between the number 2 and the number 3. And the units of the number 3 there's no interval between them. These things simply have no dimension of space. They're considered by Euclid as being to one another as a whole is to its part, or as a part is to its whole. One is a multiple of the other, which is measured by the other a certain number of times. And one is a part of another, which measures the whole of the other a certain amount of times. These things are thought of as whole and part, and nobody in arithmetic would ever think about dividing 5 by 3. Unless they were trying to distribute drachmas amongst a number of people. Unless they were dealing with accounting. These things... Unless they're dealing with accounting. Then you may want to have fractions. But in arithmetic, there's no need for fractions. We have many more difficult things to do with numbers than to divide numbers that are not... Divide a number that is not a multiple of what it's being divided by. There are other proportions and ratios which we seek, which have no sense. The problems in Euclidean arithmetic don't even make sense if you think of all numbers as divisible by all numbers. We're looking for a mean proportion between two numbers, such that one is to the mean that we're looking for as the mean is to the other. A number between two numbers, which is to the lesser as it is to the greater. We're looking for a number that has the same ratio to one number we're looking for a number between A and B such that A is to the number we're looking for as it is to B in the same ratio. We don't have time to be doing accounting and computing fractions and decimals. Because believe me, the more advanced Euclidean arithmetic that we find in his later books of the elements are replete with arithmetical theorems which the most advanced mathematicians of today would find very, very difficult. These cannot be breezed over. These are not childish theorems. Though you may think we're talking about triangles. We move a couple books forward. The elements of Euclid could occupy a person's mind for decades. And only Euclid looked on beauty. Some English poet, probably an early modern English poet, said only Euclid looked on beauty. Now, the procedural difference between those paradigms of mathematics reveals the characteristic manner of each. I mean that the procedures of calculation are absent from Euclidean mathematics, as there is no use of either numbers or equations in Euclidean geometry. Whereas the modern mathematics treatment of geometry consists in a substratum of equations. As even of the algebraic treatment of geometry consists entirely of equations. Where in Euclidean geometry, there's no numerical values. There's nothing calculated. Only syllogistic proofs. The problems are for construction, how to draw a certain figure. But we're concerned with the theorems, the syllogistic proofs. In that case of algebra, geometry is performed entirely in equations. Whether they're problems, proofs, the same procedures, even if they're performing a proof, what they give you is an equation and every step is just a rule for manipulating the signs of the equation, which is the same procedures of calculation. Doesn't look to me like an inference of pure reason. When philosophers speak of mathematics as an a priori science, or as a demonstrative science, or as a deductive science, of an a priori science that makes inferences with pure reason. Those philosophers were talking about something different than the manipulating of the science of equations. The philosophers of old who would exalt mathematics as the exemplar of a priori reasoning. We're talking about a kind of mathematics very different from that which passes as mathematical knowledge in our day. They weren't talking about calculation, nor should proofs be indistinguishable from calculation. Whereas today, arithmetic is hardly distinguishable from calculation. And arithmetical proofs are things, the steps of which consist of the same procedures of manipulating the signs of equations. The same procedures of calculation. These are not inferences of pure reason. There's no conclusion inferred from premises. There's never a middle term, first of all. You cannot say all A is C without a middle term. What do they like to do? They like to say something like, if A, then C. If A, then C. No. You cannot say, first of all, what's the subject, what's the predicate? You cannot say all A is C unless one premise states that all A is B and all B is C. If all A are B and all B are C, then it necessarily follows that all A are C. You need a middle term to draw an inference. You can't just say, if A, then C. If what is A? If A is what? If what is C? If C is what? Which one's the subject? Is there no subject? What's being predicated of what?